Welcome! In this session, we'll explore the problem titled Minimum Number of Moves to Seat Everyone. This is a fascinating challenge that involves optimizing movements to achieve an efficient seating arrangement. Let's dive right in. In this problem, we are tasked with minimizing the total number of moves required to seat all students. You're provided with two integer arrays, seats and students. Each element in the seats array represents the position of a specific seat, while each element in the students array represents the position of a student. The goal is to move each student to a seat in such a way that the total number of moves is minimized. A single move consists of relocating a student from their current position to a seat position, and the distance between any two positions is defined as the absolute difference, x, y. Finally, the output should be the minimum total number of moves needed to achieve this arrangement. To better understand the problem, let's look at an example. Suppose the seats array is 3, 1, 5, and the students array is 2, 7, 4. Our goal is to pair students with seats to minimize the total distance. First, we sort both arrays. After sorting, the seats array becomes 1, 3, 5, and the students array becomes 2, 4, 7. Now, we pair each student with the closest seat. For the first pair, the student at position 2 moves to seat 1, and the distance is 2, 1 equals 1. Next, the student at position 4 moves to seat 3, resulting in a distance of 4, 3 equals 1. Finally, the student at position 7 moves to seat 5, with a distance of 7, 5 equals 2. Adding up these distances, the total number of moves is 1 plus 2 equals 4. Let's consider another example. Here, the seats array is 4, 1, 7, and the students array is 3, 2, 6. After sorting the arrays, seats becomes 1, 4, 7, and students becomes 2, 3, 6. We then pair each student with the nearest seat. The student at position 2 moves to seat 1, resulting in a distance of 2, 1 equals 1. The student at position 3 moves to seat 4, with a distance of 3, 4 equals 1. Lastly, the student at position 6 moves to seat 7, with a distance of 6, 7 equals 1. Summing these distances, the total number of moves is 1 plus 1 equals 3. Now let's examine a third example. Here, the seats array is 10, 20, 30, and the students array is 15, 25, 35. After sorting both arrays, seats becomes 10, 20, 30, and students becomes 15, 25, 35. We pair each student with the nearest seat, starting with the student at position 15, who moves to seat 10. The distance is 15, 10 equals 5. Next, the student at position 25 moves to seat 20, with a distance of 25, 20 equals 5. Finally, the student at position 35 moves to seat 30, with a distance of 35, 30 equals 5. Adding these distances together, the total number of moves is 5 plus 5 equals 15. Let's now review the constraints and edge cases. The lengths of the seats and students arrays are always equal, and the size of these arrays can range from 1 to 100. Additionally, the positions in both arrays are positive integers ranging from 1 to 100. For edge cases, if all students are already seated at the correct positions, the output is 0 since no moves are needed. For a single seat and student, the output is simply the absolute difference between their positions. Lastly, the solution must handle the upper limit of n equals 100 efficiently to ensure it performs well even with the largest inputs. To begin solving this problem, the brute force approach is the most straightforward method to consider. The idea here is to try every possible pairing of students and seats by generating all permutations of the students array. For each permutation, we calculate the total moves required by summing the absolute differences between each seat and student pairing. This guarantees that we evaluate all possible assignments, ensuring correctness. However, the computational cost of this method is extremely high. Generating all permutations of the students array has a factorial time complexity of O(n), and calculating the total moves for each permutation adds another O(n). Combined, this results in a time complexity of O(n), which becomes impractical as the input size grows. While this approach is accurate, the exponential growth makes it infeasible for larger datasets, so we must look for more efficient alternatives. A much faster and more efficient strategy is the optimized greedy approach. Here, we leverage the insight that sorting the seats and students arrays allows us to pair the smallest seat with the smallest student, the second smallest with the second smallest, and so on. This minimizes the absolute differences between pairs, as sorting ensures that numbers closest in value are matched together. By eliminating the need to try every permutation, this approach drastically reduces computational complexity. To implement this method, we first sort both arrays, then compute the total moves by summing the absolute differences between corresponding elements in the sorted arrays. Sorting takes O, n log n, time, and calculating the sum of differences is O, n, resulting in a total time complexity of O, n log n. This makes the greedy approach not only efficient but also elegant in its simplicity. While the greedy approach is highly efficient, there is another strategy worth considering, the dynamic programming approach. This method involves using a DP table where each state, dp I, j, represents the minimum cost of assigning the first I students to the first j seats. To implement this, we start by sorting the seats and students arrays. Then, we iteratively fill the DP table using the relation dp I, j equals dp I1, j1, plus abs, seats, j, students, I. The final answer is found in dp n1, n1. While this approach is more generalizable and can handle additional constraints, it comes with a higher computational cost. The time complexity is O, n squared, due to the nested loops required to fill the DP table, and the space complexity is also O, n squared, to store the table. This makes it slower and more memory-intensive compared to the greedy approach, so it may not be the best choice unless additional constraints make it necessary. Ultimately, the optimized greedy approach stands out as the best solution for this problem. By sorting both arrays, we ensure that the smallest differences are paired together, minimizing the total moves required. This avoids the factorial complexity of the brute force approach and is far more efficient than the dynamic programming method. The greedy approach works perfectly here because the problem does not impose any additional constraints that would require state tracking or more complex logic. Sorting aligns the seat and student positions optimally, reducing the problem to a simple summation task. The time complexity is dominated by the sorting step, which is O, n log n, and the space complexity is O, 1, for additional space, making this method both fast and memory efficient. This balance of simplicity, efficiency, and correctness makes the greedy approach the ideal choice for solving this problem. The problem we're tackling involves two lists, one for the positions of students and another for the positions of seats. The goal is to rearrange the students so that the total distance they need to move to reach their assigned seats is minimized. Now, one way to solve this is with a brute force approach. The idea here is to calculate the total distance for every possible way of assigning students to seats and then pick the one with the smallest total distance. While this approach guarantees the correct solution, it's computationally expensive. First, we take two lists as input, one for students and one for seats. Then, we generate all permutations of the seat positions. For instance, if we have three seat positions like 2, 4, 6, we create all possible arrangements such as 2, 4, 6, 2, 6, 4, 4, 2, 6, and so on. This ensures we explore all possible ways to assign seats to students. Once we have the permutations, the next step is to calculate the total distance for each one. For every permutation of seats, we pair each student with a seat in the current ordering. Then, we calculate the absolute difference between the positions of each student and their assigned seat. These differences are added together to get the total distance for that permutation. To keep track of the smallest distance, we use a variable called min_distance, initialized to infinity. As we compute the distance for each permutation, we compare it with min_distance, updating it whenever a smaller total distance is found. Finally, after evaluating all permutations, min_distance will hold the smallest possible total distance, which is our result. For example, if the input lists are students equals 1, 3, 5, and seats equals 2, 6, 4, we would compute the total distance for each possible assignment of students to seats. To illustrate, let's say the permutations of seats are 2, 6, 4, 2, 4, 6, 4, 2, 6, and so on, resulting in 6 permutations in total. For each permutation, we calculate the total distance by pairing students with seats. Take the permutation 2, 6, 4 as an example. the assignments would be 1-2, 3-6, and 5-4. The total distance is the sum of the absolute differences, abs 1 to 2, plus abs 3 to 6, plus abs 5 to 4, which equals 1 plus 3 plus 1, giving us a total of 5. We repeat this process for all permutations, comparing the total distances to find the smallest one. The permutation that yields the smallest total distance gives us the optimal arrangement, and the corresponding distance is our result. This brute force approach is correct because it systematically evaluates every possible way to assign students to seats, ensuring we find the optimal solution. However, its computational complexity is quite high. Generating permutations has a factorial complexity of O(n), where n is the number of seats or students. Calculating the total distance for each permutation adds an additional O(n), resulting in an overall complexity of O(n). *n. This makes the approach impractical for larger inputs, such as when there are more than 10 students or seats. To address this, we can turn to optimized approaches, such as sorting-based greedy algorithms. These methods reduce the complexity to O(n log n), by recognizing that aligning the positions of students and seats in sorted order minimizes the total distance without needing to explore all permutations. Additionally, we rely on simple data structures like lists for storing positions and temporary variables like min_distance for tracking the smallest distance encountered. When implementing this algorithm, we also need to consider potential edge cases. First, if the number of students and seats is unequal, the algorithm should either raise an error or handle the mismatch appropriately. Another case to consider is when positions include negative values, such as -3, -1, 2. The algorithm must handle these correctly, as the concept of distance still applies to negative positions. Finally, if either the students or seats list is empty, the algorithm should return 0 or indicate that the input is invalid. Addressing these edge cases ensures that the solution is robust and works for a wide range of scenarios. The problem asks us to minimize the total number of moves required to seat students to their respective seats. Each move is calculated as the distance between a seat and a student. To minimize the total distance, we can follow a greedy approach, sort both the seats and students lists in non-decreasing order. By pairing the smallest seat with the smallest student and so on, we ensure that the total distance is minimized. The code begins by sorting both the seats and students lists. This step ensures that we align the smallest seat with the smallest student, the next smallest seat with the next smallest student, and so forth. Sorting has a time complexity of O(n log n), where n is the length of the input lists. Next, we initialize a variable total_moves to 0. This variable will store the cumulative distance as we iterate through the lists. Using a simple for loop, we calculate the absolute difference between each corresponding pair of sorted seats and students. This absolute difference represents the number of moves required for a student to occupy a seat. We add this difference to total_moves in each iteration. Finally, the function returns the value of total_moves, which represents the minimum number of moves required to seat all students. This solution is efficient and leverages sorting to achieve the desired optimal pairing. The overall time complexity of the solution is dominated by the sorting step, making it O(n log n). The space complexity is O(1), since we do not use any extra data structures apart from the inputs. This is the Java implementation of LeetCode problem number 2037, minimum number of moves to seat everyone. The logic is equivalent to the Python solution, where both arrays, seats and students, are sorted to minimize the total distance. The main difference lies in Java's syntax, such as using arrays.sort, for sorting and type declarations for variables. The method calculates the sum of absolute differences between corresponding elements in the two sorted arrays, resulting in the minimum number of moves. Here, we start with our first example where we want to calculate the minimum number of moves required to seat everyone. The inputs are two arrays, seats equals 3, 1, 5, and students equals 2, 7, 4. Initially, our variable total_moves is set to 0, which will keep track of the total distance students need to move to their assigned seats. The first step is to sort both arrays. By sorting, we get seats equals 1, 3, 5, and students equals 2, 4, 7. Sorting ensures that we can pair the smallest available seat with the closest student, minimizing the overall movement. Now, with both arrays sorted, we're ready to calculate the total moves step by step. To calculate the total moves, we iterate through both sorted arrays. For the first pair, seats, 0 equals 1 and students, 0 equals 2, the absolute difference is abs, 1 to 2 equals 1. Adding this to total underscore moves, we get total underscore moves equals 1. Next, for the second pair, seats, 1 equals 3 and students, 1 equals 4, the difference is abs, 3 to 4 equals 1, so total underscore moves becomes 2. Finally, for the third pair, seats, 2 equals 5 and students, 2 equals 7, the difference is abs, 5 to 7 equals 2, giving us a final total underscore moves equals 4. Thus, the total moves required for this example is 4. Moving to another scenario, suppose the seats and students are already aligned, as shown in example 2. Here, the input is seats equals 10, 20, 30, and students equals 10, 20, 30. In this case, we begin with the initial state where seats equals 10, 20, 30, and students equals 10, 20, 30. The total moves are initialized to 0. Sorting both arrays doesn't change their order, as they're already sorted. So, seats and students remain 10, 20, 30. Now, let's calculate the moves. For the first pair, seats, 0 equals 10 and students, 0 equals 10, the difference is abs, 10 to 10 equals 0. Adding this to total underscore moves, it stays at 0. For the second pair, seats, 1 equals 20 and students, 1 equals 20, the difference is abs, 20 to 20 equals 0. Again, total underscore moves remains 0. Finally, for the third pair, seats, 2 equals 30 and students, 2 equals 30, the difference is abs, 30 to 30 equals 0. The total moves are still 0. Since no moves are needed, the result for this example is 0. Now, let's explore another scenario where all the elements in both arrays are identical, as shown in example 3. In this example, both seats and students are 5, 5, 5. The total moves start at 0. Sorting these arrays doesn't change their order, so the sorted state is still seats equals 5, 5, 5, and students equals 5, 5, 5. Since all the elements are identical, there's no need for any student to move. Now, let's calculate the moves. For the first pair, seats, 0 equals 5 and students, 0 equals 5, the difference is abs, 5 to 5 equals 0. Adding this to total underscore moves, it remains 0. For the second pair, seats, 1 equals 5 and students, 1 equals 5, the difference is again abs, 5 to 5 equals 0, so total underscore moves is still 0. Similarly, for the third pair, seats, 2 equals 5 and students, 2 equals 5, the difference is abs, 5 to 5 equals 0. The total moves, therefore, remain 0. The result for this example is also 0. Now, let's summarize some key observations from these examples. From these examples, we can make a few important observations. First, sorting the seats and students arrays is crucial for minimizing the total moves. Pairing the smallest seat with the smallest student, the second smallest with the second smallest, and so on ensures that the distances are minimized. Second, the use of the abs function helps calculate the absolute difference between a seat and a student, which represents the cost of moving a student to that seat. Finally, the algorithm is efficient, with a time complexity of O, n log n, due to the sorting step, followed by an O, n, loop to calculate the moves. This makes it suitable for larger inputs while still ensuring optimal results. To analyze the time complexity of the solution, we start by considering the operations involved. First, we have to sort the seats array. Sorting an array of size n requires O, n asterisk log, n, time. Similarly, sorting the students array also takes O, n asterisk log, n, time. Once the sorting is complete, we calculate the total minimum moves. This is done using a for loop that iterates through both the seats and students arrays. For each pair of elements, we compute the absolute difference, which takes constant time, O1. Since the loop runs for all n elements, this step has a total time complexity of O(n). Combining these, the sorting operations contribute O(n asterisk log n plus O(n asterisk log n), which simplifies to O(n asterisk log n). The summation step, being O(n), is dominated by the sorting operations. Therefore, the overall time complexity of the solution is O n asterisk log n. Now let's look at the space complexity. The solution's space complexity depends on the resources it uses during execution. The input arrays, seats and students, do not consume additional space because any modifications, such as sorting, are performed in place. This means no extra copies of the arrays are created. Additionally, the algorithm uses only a few temporary scalar variables, such as total underscore moves and the loop counter I. These variables require constant space, O1. Since no additional data structures are used and sorting is done in place, the space complexity of the solution is O1. When comparing the optimized approach to a naive or brute force solution, the improvement in efficiency becomes clear. A naive approach would involve generating all possible permutations of the student's array to calculate the total moves for each permutation. Generating permutations alone takes O(n) time, and for each permutation, calculating the moves requires O(n) time. This results in a time complexity of O(n)(n), which becomes computationally infeasible as n increases. In contrast, the optimized approach sorts the seats and students arrays first, ensuring that the smallest differences are paired to minimize the total moves. By avoiding the need to check all permutations, the optimized solution achieves a time complexity of O(n) log n, making it significantly more efficient and practical for larger inputs. The time complexity remains consistent across all cases due to the dominance of the sorting step. In the best case, where seats and students are already sorted, the algorithm still performs the sorting operation, resulting in O(n) log n. In the average case, the time complexity remains O(n) log n because sorting is always required. In the worst case, where the arrays are in reverse order, the sorting algorithms still run in O(n) log n, and the summation step takes O(n). Therefore, the time complexity is O(n) log n in all cases. Mathematically, this is because modern sorting algorithms, such as timsort, achieve O(n) log n in both average and worst cases, and the O(n) summation step is negligible in comparison. Regarding space complexity, the algorithm uses no additional space beyond the input arrays and a few temporary variables, keeping it at O1. When tackling this problem, there are several common mistakes to watch out for. First, a major issue arises when sorting is ignored in greedy approaches. Pairing students and seats without sorting both arrays can lead to suboptimal results because the greedy strategy relies on the arrays being sorted to minimize the total distance. Another frequent error is relying on brute force for large inputs. While brute force explores all possible pairings, it has a factorial time complexity, which is impractical for larger values of n and can result in time limit exceeded errors. Additionally, some make the mistake of using the wrong distance metric, assuming Euclidean distance instead of Manhattan distance, which is the absolute difference in positions and the standard for this problem. It's also important to handle duplicate positions carefully. For instance, if multiple students or seats share the same position, failing to account for this can lead to incorrect results or inefficient solutions. Lastly, overlooking edge cases is a common pitfall. Scenarios such as having only one student and seat, all positions being identical, or dealing with negative positions should be addressed to avoid incorrect outputs or runtime errors. This type of problem often comes up in interviews, so it's important to recognize key patterns and strategies. A critical insight is that minimizing the sum of absolute differences is a classic greedy algorithm problem, where sorting the arrays is a fundamental step to find the optimal pairing. Another consideration is the trade-off between correctness and efficiency. While brute force guarantees the optimal solution, it is computationally expensive and impractical for real-world constraints. Greedy approaches, and in some cases dynamic programming, offer significant optimizations. During interviews, always clarify assumptions. For example, confirm with the interviewer that Manhattan distance is the required metric, as it's the most common. Additionally, ask about constraints such as the maximum value of n or whether negative positions are allowed. Testing edge cases is another crucial step. Demonstrating the ability to handle single student scenarios, identical positions, or other edge cases shows robustness and attention to detail, which interviewers value. Finally, studying related problems like two-city scheduling or campus bikes too can help you understand variations and deepen your problem-solving skills. There are alternative approaches to solving this problem, each with its own trade-offs. The brute force approach, while conceptually straightforward, involves trying all possible permutations of pairings. This guarantees the optimal solution but has a time complexity of O(n), which is computationally expensive and only feasible for very small input sizes. A more practical solution is the greedy approach, which involves sorting both arrays and pairing corresponding elements. This method has a time complexity of O(n log n) and is efficient for most problem constraints. For variants of this problem where additional constraints are introduced, such as assigning weights to pairings, dynamic programming can be used. DP allows you to track optimal pairings while handling more complex requirements, though it increases implementation complexity. Ultimately, a key insight is that sorting and using a greedy pairing strategy often leads to the optimal solution for minimizing Manhattan distances. However, always be mindful of edge cases and ensure that constraints are clarified when discussing your approach in an interview setting. To wrap up, we reviewed the key approach to solving this problem, focusing on sorting and summing absolute differences for efficiency. Remember the significance of balancing time and space complexity in algorithm design. Thanks for watching, and we'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!